section 9.3, communication and dominance matrices. The first area we're going to cover is communication. And with communication, we look at how different entities or objects communicate with each other. So we'll use communication diagrams and matrices to show the connections. Some examples include computers on a network and friendships on Facebook. In the second part of this section, we'll cover dominance. Here we'll look at to rank in order from best to worst various objects that are in a competition. So an example would be footy teams within the Tallangatta League. So firstly, let's take a look at communication. Here we have computers A, B, C and D, and they're shown on this communication diagram. Computer A can directly communicate with computer D, but computer D cannot directly communicate with computer A, and that's shown as the straight line with the arrowhead going from A to D. If we look at the link between A and C, you can see there's a straight line with two arrowheads. This tells us that computer A can directly communicate with C, and computer C can directly communicate back to A. So this is an example of a two-way communication between A and C, whilst between A and D, we have a one-way communication, that is that A can directly communicate with D, and that being it only, not D going back to A. Now with this diagram, we can represent these connections in a matrix format. So here we have a matrix, and you can see we've got the computers A, B, C and D, and this is the from position. And along the rows here, again, we've got computers A through to D, and that's the to position. So if we look at from A, you can see that from A, we can communicate directly with D, and we can communicate directly with C. So every time that there is a communication to another computer, we'll represent that as being a 1. If there's no direct communication, then we'll represent that as being a 0. So as an example, from A to B should be a 0, whilst from A to C should be a 1, and A to D should be a 1. Please also note that we don't consider a communication to itself. So across this leading diagonal here, you will see that we have zeros because the computers cannot communicate with themselves. So again, taking on the position from A, here we are from A to A, we place in a 0 because we cannot communicate with ourselves. From A to B, there is no direct communication, so we place a 0. From A through to C, there is a direct communication, so we place a 1. And from A to D, there is also a 1. And we just work our way through. So then we go from the position of B, position of C, position of D, and so on. Now what you'll notice is that with this communication matrix, it's what we call binary, in that it consists of only 1s and 0s. The leading diagonal will always consist of 0s. And if the diagram, the communication diagram, has connections with double head arrows everywhere, that means that every link is a two-way communication. So if you have that situation where every single link between the objects is two-way, then what you'll see is that this particular communication matrix, or not this particular one, but a communication matrix, will be symmetrical around the leading diagonal. And this one obviously isn't. And the reason for it is because back at our original diagram, some of these communications are just one-way communications. They're not all two-way. And that's summarised in this blue box here. So looking at this example, we have 4 cities, cities A, B, C and D, and we're considering direct flights to the other cities. So we've got from city A, there is a direct flight to city B, and there is a direct flight to city C. If we consider from city D, we've got no direct flights to A direct flight to B, a direct flight to C, and none to D. Of course, we would not fly directly to the same city. So if we started from D, we wouldn't directly fly to D. So it makes sense that there's a 0 there. You can see that there are zeros in this leading diagonal. You should also see that this matrix is not symmetric around that leading diagonal. So therefore, in some cases, we're going to have one-way communications, and in others, we're going to have two-way. it's certainly not going to be all two-way communications, and that's why it's not symmetrical. Our first job in part A is to create ourselves a diagram from the matrix. So it's in reverse to what we did before. So we've got the various cities A, B, C, and D. And if we take the perspective of A, you can see that we've got ones going to B and C. So from A, we're going to B, put the arrowhead on, and then from A, draw a line down and put an arrowhead down the bottom here, showing that we can go from A to C. Then we move across to B, do the same thing. You can see there that from B, we only have one direct communication to D. So from B, we can only go directly to D. And you'll see here that with B, all of the other cities have direct flights into it, okay, but from B, we can't get to A, we can't get to C, we can only get to D. And we just repeat that, working our way through. So here we have M, which shows our communication matrix. And then in B, what we're asked to do is have this K matrix, and it is a row matrix consisting of 4 ones. So this is going to be a summing matrix. And we're asked to evaluate K times M. So we place the summing matrix before this communication matrix, and you'll see we'll get this result. So considering that, what we've got going on here is that we've got one row by 4 columns being multiplied by a 4 by 4 matrix. So the two inners are 4s, so that's possible, and our result will be one row by 4 columns, so that's that matrix N here. What does the 2, 1, 2, 2 represent? It's the addition of these columns. And that's what this is about here. What is it that it actually gives us? So basically what we're seeing is that with that N matrix, it tells us there from city A, there are 2 direct flights to the other remaining 3 cities. From city B, there is only 1 flight to the other 3 remaining cities. From city C, there are 2 flights to the other 3 cities. And the 2 here means that from city D, there are 2 direct flights to the other cities. With D, which of these cities has the fewest direct flights? And you can see that it's city B. So looking at this example, what we have are 2 diagrams, so diagram 1 and diagram 2, and we're asked to create a communication matrix for each one. Now you can see here that we have 5 different objects, A through to E, A, B, C, D, and E, and we do the same thing here for our rows. And what's really important is that we recognize that that's the from up the top, and then this is to the to. Okay, that's really important to get that right. And basically we start from the perspective of A. Now from A, where are we going to? We're going to B directly, we're going to C directly, and we're going to D directly. Everywhere else we should have zeros, and that's shown here. B, C, and D, everywhere else zeros. And we just work our way through the diagram. So now we go from B. From B, we can directly go to A. We can't go to ourselves, so it'd be a 0 there. We can go to C. You can see that with that arrowhead. We can't go to D, but we can go to E. And there's that column that shows that perspective, so it's the from. And we work our way through the diagram and placing 1s and 0s everywhere. Of course, along this leading diagonal, you should always have 0s because we cannot communicate with ourselves. What you'll see in that first diagram is that there's a variety of one-way and two-way communications. So one-way, remember, is just shown with the 1 arrowhead, where two-way, you've got the 2 arrowheads. So that's a two-way communication between A and B, whilst this is a one-way communication from A to C. With our second diagram, we do exactly the same process. And so we start from A, we get all the perspectives where we got direct communications with, B, C, D, and we just go filling in our columns. Again, very important to get the from and the to right. But what you'll notice is that with this second diagram, that all of the lines have double arrowheads. So each one of these communications is a two-way communication. You can see that. So when we take a look at the matrix that's produced, we've got zeros going through the leading diagonal, but what you'll also see is that it's symmetrical around that leading diagonal. So here and here, and then that position and that position, and then these two positions either side, and so on. So it's symmetrical around that leading diagonal. And the reason for that is because each of the communications are two-way. Now, this diagram wasn't given to you in your notes, so you just need to pause this now and write that diagram in. But basically, we've got different towns, A, B, C, and D. And then the distances, in fact, it's the amount of minutes it takes to drive directly between those two towns. So directly from town A through to D takes 56 minutes. Going from A directly to B will take 23 minutes. So obviously, if we go from A to D, the assumption is that there is a road that would take you directly to D, that you don't need to go through any of the other towns. Although you could go through town B, then to town D to get there. But the way, if we take this particular road directly from A to D, it'll take us 56 minutes. And what's interesting in that example I just showed you is that if we went from A through to B and then through to D, that'd be a total of 53 minutes, which would actually be quicker. But we're only considering at this stage the direct communication, so the direct links between the towns. And again, we need to show that in a matrix diagram. We've got the towns A, B, C, and D, and reproduced here, from and to. So we're filling it in as a column each time. So you've got from A to C will be 28 minutes. So from A to C, 28 minutes. From A to B, 23 minutes, and so on. So in this case, it's not a binary matrix, but it is showing all the distances there, and it's quite useful. But you will see that we've got zeros coming through here, and the reason for that is that we're not considering starting from town A and then directly driving back to town A. So far, what we've been taking a look at is just one-step communications. So here we've got a communication diagram between A, B, C, and D, and they show all the one-step communications or direct communications. If we consider the idea of going from A to B, you can see that with just one step, that's impossible for us to achieve. But if we go from A to B, it is possible if we do it in two steps. So if we start from A, we can go down through to D and then go up to B. So we can get from A to B, but we do it in two steps. And the path that would take would be A, D, and then B. If we now consider the idea of going from B to D, so as you can see, we can't directly go from B to D, so there's not a one-step communication between B to D. But if we start from B, what we can do is go down through to C, up to A, and then down through to D. So in this way, we can go from B to D, but we do it in three steps. So 1, 2, and then 3. Now you can imagine that we can create ourselves an M matrix here, a communication matrix that shows all the one steps. If we want to consider all of the two steps, we'll just take that M matrix and raise it to the power of 2, and that will give us the number of two-step communications between the various objects. Same idea if we look at the three steps. We can just take the M matrix, the matrix that shows all the one-step communications, and raise it to the power of 3. And obviously we do that in our CAS. M4 the same, and that repeats. Now if we want to consider all of the one-step and all of the two-step communications, so that's combining the two, all of the one-steppers and all of the two-steppers, then we just take the M matrix, which shows us all the one-step communications, and we add to it the M squared matrix, which shows us all the two-step communications. And the same thing here if we've got all of the one, two-step, and three-step communications. So that's what we'll refer back to, and this will become clearer with the example below. Also, when we start squaring or tripling raising it to the power of 3, the original M matrix, what you'll see is that we'll start having non-zeros going through this leading diagonal. Now, for most parts, it won't make sense that we want to communicate with ourselves, or computer A would want to communicate with computer A. It'll be illogical, and therefore we should, in most cases, ignore the values that are shown in this. So this example here should clear things up for us. We have ourselves a communication diagram. So you can see we've got objects A, B, C, and D, and all the links between them. And we've got the related M matrix, which is the communication matrix. It shows all the one-step connections. So these are the direct connections from object A to A, B, C, D, from B, C, and D. So it's very important that you get the from right and the to right. In the first part here, what we need to do is show all the two-step communications, or show the two-step communication matrix. So what we do using CAS, of course, is to simply put in that M matrix. So we put what's inside those square brackets into our CAS, and we raise it to the power of 2. So that's that M matrix raised to the power of 2. And that's the result for it. So this shows all the two-step links from A through to all of the other objects, from B, from C, and from D. And you can see it's different than what we originally had with the M matrix. So these are all the two-steppers. Now the second part of A here is asking us the number of two-step self-communications from A to A. So if we look at our two-step matrix, you can see that there is one path that takes us from A back to A that involves two steps. What is that path? It's A, C, A. So if we start from A, we can go down to C and then return back to A. So that's a two-step way of starting from A and getting back to A. And that must be the only one, because there's only a 1 in that M squared matrix, which shows us all the two-step communications. Part 3, the number of two-step communications from A to B. Okay, so from A to B. So there should be two paths that we should be able to create that involve two steps. And these are the paths ADB and ACB. So let's go back to the original communication diagram and look at going down ADB. So if we go A, down to D, then to B. So that works, and that involves two steps. The second one listed was ACB. So here we start at A, we go down to C, and then up to B. So they should be the only two-step communications that take us from A to B. And we know that because of the M squared matrix. Now we're after the three-step communication matrix. So we take our original M matrix that shows us all the direct connections, and we just raise that to the power of 3. There it is there, to the power of 3, and that's what we get. And we're interested in the number of three-step self-communications from A to A, listing all of the paths. So from A to A, you can see there's only one three-step jumps, or three steps that take us from A to A. And if we go back to our communication matrix, let's look at what that is. We can go from A down to D, across to C, and then back up to A. So we start from A, we get back to A, and it involves three steps. And that is the only one that's possible. And again, we know that because if we look at our M cubed matrix, there's a 1 from A to A. All right, this time what we're asked to do is take a look at the number of three-step communications from C to B. So if we go from C to B, you see that there should be three paths that are possible that involve three steps. And they're listed here. Let's just go through one. You can double check these, of course, but our first one there is CADB. So again, going back to our communication diagram, C to A to D and then to B. You can check the rest of the numbers as well. So for part C, what we need to do is consider all of the one-step or two-step communications. Okay, so the M matrix will give us the one-steppers, and the M squared matrix will give us the two-steppers. So M plus M squared. So we're going to have our M matrix, and then we get the M matrix and we square it. And so this result here is the M squared matrix. See how they're different? It's simply this matrix squared is this matrix. If we add those two together, we'll get this matrix here. So this shows us all the communications from objects A, B, C, and D to each other, achieved either in a one-step or a two-step. The second part of this question, the number of one or two-step communications from D to C. So from D to C. So you can see that there are two. Now, the two that have been identified is a one-step of D to C, and also a two-stepper that involves D, B, and C. And you can check that again against that communication diagram at the top. So you can just go and take a look back in your notes there and verify that you can directly go from D to C, and that you can get from D to C if you go via B. And then what we're asked to do is take a look at the communications that can't be made with either one or two steps. So if a communication can be made, then what we should be seeing is that there is a number in that particular position in the matrix. So we've got numbers everywhere, but we've got a couple of zeros. So that means that from B, we can't get to D in either a one-step or a two-step communication. Also, there's a zero down here. So if we start at D, we can't get back to D in one step or two steps. All right, now what we're asked to do is to consider the matrix that will give us all of the steps that are no more than three. So that is, it's either a one step, it's a two step, or it's a three step. So here we've got the M squared, and the M cubed. Okay, so there's those matrices there. If we add all of those together, we'll get this matrix. So this shows us everything, and you can see that in no position there is there a zero. So involving either a one step, two step, or three steps, we can start from anywhere and get to anywhere. We're looking at now dominance matrices, and the idea about dominance is that we're looking at ranking in order from best to worst various objects. So this could be players competing in a tennis tournament, or this could be players competing in a one-on-one basketball competition. When we're doing this, we're only considering winning or losing. There are no draws. We use dominance diagrams and also dominance matrices to help us understand what's going on. So to begin with, just have a good read of these couple of paragraphs and this little area in the box. You'll see it refers to direct dominance and indirect dominance. And rather than just explain the notes here, I think I'll highlight the differences between indirect dominance and direct dominance with the example below. Just remember, with the matrices, we've got from and to. So if I'm in this position here and there is a 1, that would represent that player A has a direct dominance over player B. So here we have an example where 4 girls play against each other in a series of one-on-one basketball games, and these are the details given, these are the results. We need to make ourselves a dominance diagram. So I start by placing in dots for players A, B, C, and D, and then I just work my way through the information. So Abby beats Bess. So Abby beats Bess, and we draw ourselves a link with an arrow showing who has defeated who is dominant. Bess has no wins, we'll deal with that later. Kath beats Bess and Denise, so from C, we go direct dominance over B, and then a direct dominance over D. And Denise beat Abby and Bess, so from D we beat B, and we also beat Abby, A. Now you'll notice here that they are all one-way arrows. There are no two-way arrows. Okay, because with dominance, you either win or lose. There's no draws. So it would make sense that if Denise is more dominant than A, in return, A can be more dominant than D. So that's illogical. So one's better than the other. If they play off, you've got a winner or a loser. So in a sporting context, just assume that you keep on going to overtime until you do get yourself a winner. There are no draws. Now we can represent this information in a matrix format. So this is a dominance matrix, and we've got from these particular players to those players. So as an example, this particular one represents that player C has played player B and beaten them. And that's shown in this link here in the diagram. So we just take the different perspectives like we did with the communication matrix and just work our communication diagrams done earlier and just create this matrix. So if we look at B, you can see that in B situation, B doesn't beat anybody. Everybody else beats B. So along this B column, we've got a series of zeros. And then from D, you can see that D beats B and D also beats A. So we've got a 1 there and a 1 there, and then these are zeros. Now what's interesting here is that it's very easy for us to consider, the effect of, or we can all see that B is the worst player and everybody has beaten B because all the arrow heads are moving in towards B. That's fine. But what about who's more dominant out of A and C? Now A and C haven't had a game. So we've got no way of telling who is directly more dominant. However, if we look at indirect, then what we can work out is that player C has beaten player D. And now player D has beaten player A. So what we can assume there is that C is better than A. And the reason for it is this indirect dominance. So if C is better than D and D is better than A, then it makes sense that C would be better than A as well. So this is an example of an indirect dominance, where player A beating player B is a direct dominance. They've played off in a game, and A has beaten B, so directly A is better than B. That's a direct dominance, and C being better than A is an example of an indirect dominance. So C has beaten D, and D has beaten A, therefore we can say indirectly C is more dominant than A. How many wins has each person had? And then if you go and take a look back at the matrix, simply adding up the columns. So D has had 2 wins, C has had 2 wins, B has had none, and A has had 1 win. Now because C and D both have had 2 wins, we can't really say who's best out of C and D at the moment. We need to consider some more information. So what we can do now is take that dominance matrix M and we'll square it. And what this will tell us is the indirect dominances. Or it'll tell us, just the indirect, dominances only. So there's our M, we take our M matrix, we square it. And of course, just do that using CAS, don't do that by hand. And then this is our result. So if we look at our indirect dominances now, D has had 1 indirect dominance over the others, C has now had 2, B's had none, and A has had none. Now if we consider all of the direct dominances and all of the indirect dominances, we'll have some more information. So this is our original M matrix, this is our M squared matrix, so this gives us our direct dominances, this gives us our indirect dominances. If we combine the two, we'll get this matrix here, which takes care of both. And now if we add the columns together, you will see that again, player B has no dominances at all, either directly or indirectly over the others. A has 1, C has 4, and D, adding all those together, has 3. So now it's pretty clear for us that we can rank these players from best to worst. So obviously C is the best, D is next, followed by A, and then B. So we've got a clear ranking there after we consider the direct dominances and the indirect dominances.